Welcome back to the lab, everyone. So if you've ever looked up at a hanging power line or marveled at the sweeping cables of a massive suspension bridge, well, you've actually witnessed a beautifully complex physical system perfectly at rest. Today, we're going to formulate and solve these exact physical problems using modern optimization software. Now, as optimization students, you already know the real challenge isn't just understanding the physics, right? It's translating that physics into code that a computer can actually process without completely crashing. So let's just dive right into this step-by-step lab and see how one simple mathematical trick can literally save our algorithms.
Here's our quick lab syllabus for today. We'll start with the physical problem, move into discretization methods, tackle convexity and relaxation, check our algorithm efficiency, apply real-world loads, and finally, look at bridge and power line design.
All right, Section 1, the physical problem, defining the geometry of a hanging chain.
So, before we even think about writing a single line of code, we've got to precisely define the phenomenon we're studying. We're trying to find the exact equilibrium shape of a heavy, flexible chain, or say, a power line, hanging under its own weight between two supports. This resulting shape naturally minimizes the chain's potential energy. It's actually a really classic problem, one that challenged early mathematical giants way back in the 17th century. Fun fact, Galileo actually studied this shape and mistakenly guessed that the curve was a parabola. Hey, even geniuses get it wrong sometimes. But, as defined here, a flexible chain of uniform mass hanging freely actually forms what we call a catenary curve. Mathematically, that's described as a hyperbolic cosine function. And this is an absolutely crucial mathematical distinction we have to make before building our software model. Why? Because if we just assume it's a parabola, we're going to end up with completely incorrect tension models.
Moving on to Section 2, discretization methods, bridging calculus and computer algorithms.
Okay, so we know the continuous mathematical curve, but computers, they only understand discrete points and steps. To actually solve this in a non-linear optimization solver like Loco, we've got to break the chain down into manageable segments. And here is the crucial algorithmic pivot of our whole lab, choosing our discretization method. Do we use a naive approach along the horizontal axis, basically just chopping the x-axis into equal parts? Or do we parameterize the problem along the actual length of the chain itself using the variable t? Well, parameterizing along the chain's length vastly simplifies the mathematical solution. It aligns our data points with the actual physical object rather than just forcing the model onto some arbitrary spatial grid.
Now, discretizing along the horizon, the x-axis, seems totally logical at first glance, right? I mean, that's how integration is taught in basic calculus. But in the realm of computational optimization, it creates these strict mathematical constraints that act exactly like traps for our software solvers. Which brings us to a really critical question. Why exactly do numerical failures occur with these hard constraints? Well, if we treat the chain as a series of rigid, fixed-length links and force strict equality constraints into our code, an interior point method solver is going to struggle fast. It's trying to find an exact, rigid mathematical fit in a highly complex, high-dimensional space. These hard constraints act like a trap, and the solver usually just ends up wildly crashing or taking forever to converge.
Section 3, convexity and relaxation, the mathematical epiphany to solve numerical blowups.
All right, here's the climax of our lab, troubleshooting those numerical errors. If you want a step-by-step guide for your own optimization projects, here is exactly how you fix a solver crash. Step 1. Abandon the x-axis and parameterize the function along the chain's length. Step 2, and honestly, this is the magic trick, relax the rigid equality of your link constraints. Instead of saying a link must equal a specific length, change it to a less than or equal to inequality. Step 3, verify convexity. And Step 4, run the solver. Because we are minimizing potential energy, gravity automatically pulls the chain taut anyway. The inequality constraint acts like a bungee cord that gravity stretches to its absolute limit, completely bypassing the messy numerical failures of hard constraints.
So the absolutely crucial takeaway here is this. Convex optimization formulations are mathematically stable. By making that one tiny change, swapping an equals sign for a less than or equals to sign, we literally transformed a non-convex computational nightmare into a mathematically elegant breeze. The solver can now rapidly find that global minimum without a hitch.
Section 4, algorithm efficiency, comparing computational performance objectively.
Let's look at the numbers. Comparing the discretization parameter n reveals a staggering difference in computational efficiency. When chopping the chain into 800 segments using that naive horizon method, the solver takes over 500 seconds and essentially just fails to converge. But our relaxed parametrized model, it solves the exact same physical problem for 800 segments in just 1.1 seconds. No way, right? And it's not just about raw speed, it's about accuracy. If you check the dual and primal values in your source logs, you'll see the dual infeasibility drops to nearly zero super rapidly in the parametrized model. This confirms a highly accurate, efficiently converged solution, proving exactly why picking the right discretization method is a total game changer.
Section 5. Real-world loads. Adapting mass distributions for modern engineering.
Okay, so now that we have this robust software model that solves in fractions of a second, we can actually adapt it. Because in the real world, mass isn't always perfectly uniform, right? Watch what happens when we drastically alter the mass distribution by coding extra weight onto specific nodes, like say the center node and the corner nodes. Our convex model instantly adapts to find the new equilibrium shape. It brilliantly visualizes how the increased local mass drags the catenary curve completely out of its standard form, perfectly simulating the exact forces modern engineers deal with every day.
Section 6. Bridge and power line design. From abstract mathematics to massive infrastructure.
Now, when transitioning from a standard catenary chain to a massive suspension bridge, the physics actually shift. A suspension bridge's heavy roadway spreads the total weight evenly across the horizon, not uniformly along the cable itself. So, when we plug this uniform horizontal mass distribution into our parameterized solver, the mathematical shape transforms. It is no longer a catenary curve at all. The physical reality of the suspension bridge demands it becomes a perfect parabola.
And applying these exact same parametric optimization equations to power grids isn't just some academic exercise. Modeling the tension, the distance, and the sag accurately is a vital matter of public safety. We have to prevent these lines from snapping under their own tension or sagging dangerously low into trees.
Plus, when the wind hits those lines, they don't just sit there. They experience complex, intense vertical vibrations known in the industry as galloping. By mastering the continuous catenary equations and correctly discretizing them into a convex model, structural engineers can predict this dangerous galloping behavior. They can determine exactly which nodes along the physical wire require the installation of vibration dampers to cancel out those resonant frequencies. Pretty amazing, right?
So, to wrap up today's lab assignment, here are your actionable recommendations. First, when modeling complex physics in software, always prioritize convex mathematical formulations. Second, parameterize along the object's length rather than an arbitrary axis to massively increase computational efficiency. Third, use constraint relaxation, turning hard equalities into inequalities to completely bypass non-convex numerical failures. Fourth, always check your dual and primal values to interpret the accuracy of your convergence. Basically, if your dual infeasibility doesn't approach zero, your model needs adjusting. And finally, remember that a robust model easily allows you to adjust mass distributions to adapt to real-world loads.
Which leaves us with this final thought. We literally just took a physics problem that crashed a computer and solved it in 1 second by changing a single equal sign to a less than or equal sign. So what other complex physical systems could you instantly solve just by relaxing one rigid equality into an inequality? Keep that in mind for your next software build. Thanks for joining this lab and keep optimizing.